This is Berkeley Talks, a UC Berkeley news podcast from Strategic Communications at Berkeley. You can follow Berkeley Talks wherever you listen to your podcasts. New episodes come out every other Friday. You can find all of our podcast episodes with transcripts and photos on UC Berkeley News at news.berkeley.edu/podcasts.
Welcome to Brilliance of Berkeley. This is LNS 110. I'm Crystal Chern. I'm your lecturer. I'm an engineering researcher and educator here at Berkeley. So welcome. We're all in a really extraordinarily lucky position this semester to take class from the most distinguished researchers both in and outside of your majors. This is a once-in-a-lifetime chance, unless in a decade from now you find yourself in my shoes. Each of these professors are working on one of the world's deepest, most difficult, most pressing issues, from climate change and sustainability in the digital age, like we'll see today, to NASA space exploration, to the human genome, to the human psyche, to economic development, and much, much more. That means there's hundreds, thousands of people clamoring for their attention every day. And the fact that they're here with you means that you're important enough and you have the ability to be the next leaders in these issues. And they really want to connect with you. So, take advantage of this chance. I hope this class allows you to think more broadly and hopefully and courageously about your college experience than just trying to keep up with your colleagues. I hope it inspires you to stop, wonder, and question rather than stuffing yourself into a mold. It took me all the way up into graduate school to do this. But the sooner you start, the sooner you might have the confidence to say, I'm here at Berkeley to contribute to its brilliance, not just to keep up. So I'm going to introduce Omar, Professor Yaghi. He asked for a very short introduction so that he could talk to you a little bit longer. But he is a university professor here at UC Berkeley. And as you might know, he just won the Nobel Prize in 2025, Nobel Prize in Chemistry. And without further ado, Professor Yaghi.
Okay, thank you very much for the introduction. It's always a pleasure to talk to students. And today you saw two titles, one about carbon capture and water harvesting and AI. And now you're seeing scarcity to abundance. I will still talk about those applications, but I want to frame it in light of the Nobel Prize. I gave that title before the Nobel Prize, but in light of the Nobel Prize, I want to share with you sort of my scientific journey so that perhaps not to necessarily emulate, but rather as an example of how science can transform our lives from scarcity to abundance. So let me start by saying that I was born in Amman, Jordan, and raised in Amman, Jordan. And I come from a small village in Palestine called Mesmia. And I attended a private school in Amman until I was 15. It was Bishop School. It had Muslim kids and Christian kids working together. And my parents spent every dime that they ever earned to put us kids into this school. So education was everything. To refugees, obviously. Well, this is me, okay, with lots and lots and lots of hair, and I'm holding a book, okay, and behind me is a room where we all lived. I come from a family of 10 kids, and the parents, and not only that, but we also lived with the a few cattle that we raised for living. And between us and the cattle, there was sacks of feed. These sacks of feed were a special mix of hay and seeds that, or corn that or wheat that the cows were. This was a special recipe of my family to raise the best meat. So I'm sort of in the middle. I'm fourth from the bottom. Um, and uh, and uh, and so today's lecture is about what happens between 1976 and now. Okay, and how does one go from a world of scarcity where we hardly had anything? I mean, we didn't have electricity or water or anything like that. We were, I was a child of refugees. You can imagine the hardship growing up in that environment. So how does one go from here to here? Okay, so the first thing that I want to talk about is my school. I didn't like my school. I didn't like the teachers. I didn't like anything about it. It was because it had all the rich kids and I was the poor kid and I was not really treated as well and so on. But I was a very quiet child. And I just observed. It seems like my whole childhood was about sitting in a corner doing my studies and just observing everything around me. I didn't play with the other kids. I didn't play with my brothers and so on and sisters growing up. So I was a very quiet child. In fact, at some point, my parents thought there was something severely wrong with me. They're probably right. We haven't figured out what it is. Um, and and so you look around you with all this misery, and one day, and I tell this story because it's very important to understand that your love, your passion, comes from the most unremarkable situations. For me, my great break in life was when I went into a library that was supposed to be closed in my school, and there I opened a book and I saw molecular drawings. And I didn't know they were molecules. I was 10 years old at the time in third grade. So I didn't know what they were, but somehow I was captivated by them. And I thought I discovered something that nobody has ever seen before. And so I went home that day, determined that this was my secret. And so bit by bit, I started learning about them, and there were molecules and there were the constituents of everything around us, living and non-living. Well, immediately I thought, you can't tear yourself away from that. And I was in love with chemistry. That was really it was basically my passion, and it became my interest, and eventually it became my life. There's another break that I had in my life, which was the Yaghi meat shop in the middle of Amman. Okay, this was actually in the middle of Amman. It was between our home and the school. So whenever I go to school in the morning, I pass by, and when I come home from school, I pass by. They were about 3 miles apart. And I would help my father with the chores in the shop. And there I learned the work ethic. My father was a very firm father who wanted everything done right and done perfectly. And my students now will understand why I am the way I am, and they can blame him. But I would clean, let's say, the glass, the showcase, and he wanted to make sure there are no streaks. And I learned that if you don't do something unless you do it right and you do it completely. So this aspiring to do a perfect job was very, very important. Then one day I came into the shop from school, and my father said, "You're going to America." I was 15 years old. I only finished 9th grade. And I said, "No, I'm not going to America. I want to finish high school here, college here." And he had his methods of forcing me to do it. And in the end, next thing I know, I was delivered on a KLM flight through Amsterdam to New York City. And there, somebody picked me up to go to Troy, New York, where an uncle of mine used to be a few years earlier, and an older brother was at the time in Buffalo. But I called back home and I said, "What do I do now?" And they said, "Well, take the grades that you have from your school in Jordan and show it to the nearest college." Well, the nearest college was Hudson Valley Community College. I mean, I felt very odd that I would just go there. And so and this is the beauty of the American system, it collects everybody. Okay, everybody can go to college. So they said, "Okay, we'll just give you some classes at freshman take. And so I took calculus, chemistry, and biology, and English as a second language. And at the end of that term, I went back and I said, look, I did okay. Can I get admitted? And they admitted me. And after 2 years, I transferred to SUNY Albany. At SUNY Albany, I discovered the lab. And there I did 3 undergraduate projects in parallel. I was so hungry to play with molecules, and you know, these chemistry labs are disgusting. I mean, they're not a very hospitable environment. They're dirty and smelly and everything like that. But somehow I was attracted. I was attracted to them. And I was really, I began to fall in love with the beauty of molecules and everything about chemistry. And in my organic chemistry lab, when you do an organic compound crystallization, you see crystals falling from the liquid just like snowflakes. Well, I looked at that and I thought, oh my God, that is so amazing. It's almost like life's perfection is encapsulated into these crystals. And indeed they are. Crystals are perfect form of matter. And so my whole life was centered around the beauty of molecules and the beauty of crystals, and nothing else mattered. The only thing that mattered that I was in a lab, and that lab allowed me to do stuff, to start learning about chemistry. This is an example. If any of you have done organic chemistry, you probably have done this. And it's the beautiful thing about science is that it looks very humble and very simple, but it's very deep. Okay, and that's what matters. And so I'm in love with crystals. And so finished my undergrad, and I wanted to go to graduate school. Of course, the parents were pulling at me to go to medical school, to become something useful like an engineer, because chemistry is not it's not a very sensible discipline if you want to make money. And I was fixated on the beauty of molecules. And again, of course, they never knew what was wrong with me. I chose my graduate school not because of prestige of necessarily the institution or the professor or anything like that, or I had a blueprint for success. I chose it because I saw this kind of molecule. I thought it was very attractive, a ball-looking shaped molecule, and I thought, wow, I'd love to work on that. My message here is that you don't have to be deeply intellectual to fall in love with stuff, okay? It doesn't have to be a full-fledged plan, well thought out and rational, okay? That your passion in life can come from the most humble scenarios and the least maybe intellectual circumstances. Falling in love is not very logical. That was my relationship with these molecules. And so I thought, okay, I'll go to this university and I'll meet, that was the University of Illinois, Urbana. I'll go to this university and meet the professor. The professor is nice. I'll join his group. I'll apply and join his group. Well, he was very nice. He interviewed very well. But he was a very firm professor. He was uncompromising about quality, about rigor. You had to do and redo and data, and it was like my father all over again. But now more about science. So my task, and again for the students, my task was to deprotonate this monster. Okay, just take one proton out. That is the simplest chemical reaction that anybody can do, right? You couldn't have a more trivial experiment to try. So I was supposed to make this monstrosity H3V10O28 3- to H2V10O28 3-. And I tried for a whole year and with no success. I started questioning whether my love for molecules was just some superficial, dumb passion that maybe I did not have the intellectual skills, maybe I did not have the skills, maybe I didn't. It was not really my calling, and I started questioning whether chemistry was really my direction. But throughout my life, I always persisted, and I always did things once more. I always tried and tried until everything was perfect. Even when I was in school reading a poem, I would read it, memorize it, write it until it was absolutely perfect, right? So doing something over and over again, I developed skills that way. I developed a skill, a craft that no one can compete with. Okay, when you do something over and over again, you perfect it. It's not just repetition, you're learning every time you do it. And so at the end of the year, I had already knew what kind of color change should be, and this is the kind of color I should be getting. And I got this, and I was very, very excited. I was no longer desperate that I have to go back to Jordan because I failed, which would be a disaster, right? I mean, I didn't tell you, but I came from Jordan with all my family's savings. The embassy said, you better have some money to go to America, and we want you to get your entire family's saving, which I told them was $9,000. And they said, yes, come back with $9,000 in your name, and we'll give you the visa. So I had taken my entire family's savings with me, and failure was not an option. You could not retreat, okay? So there was a tremendous motivation to move forward. So I got it. After 1 year, I got it. But then I went to the NMR machine to analyze it. And I had predicted what the NMR spectrum should look like for this material. I mean, I was so enamored by success but the NMR spectrum was nowhere close to what I was predicting. It was just a forest of peaks, and none of them fell in the right place. So, failure. I called it failure, but then my professor said, you just made a whole bunch of new compounds, okay? Or, if you want to be blunt, you've discovered something completely new. What I got out was this gunk out of the machine. My beautiful orange compound had turned into this brown, disgusting stuff. And I was absolutely horrified about getting fired, because that's it. I mean, you were given a task to start out, and maybe the professor will say this student is not fit for an intellectual endeavor. So it was in the middle of the night, I asked one of the postdocs who used to hang out at night in the lab, I said, what do I do with this? He said, well, this looks disgusting. You better just throw it away. I can't throw it away. It's my whole year's work. So what I did is I prepped it for crystallization, and the next day I found beautiful red crystals, almost as beautiful as a diamond, a red, just beautiful shaped dark red crystals. And when we analyzed them by single crystal X-ray, they were this beautiful ball molecule. It's a ball shaped like a rice bowl. And this is another view of it, down the bowl, down the space. And there was nothing like it before. This was my first discovery. Now nobody can talk to me. I would go to the professor very confident, and I am successful, and I need to get my PhD, and so on and so forth. And this was really, to me, there was almost no, at this point, all that doubt about whether I was a chemist or not, or a scientist, or I could be a scientist, were alleviated, not completely removed, but alleviated. This is my advisor. His name is Walter Klemperer. He taught me science begins with doubt and questions. So that tells you a lot about him. Whenever you showed him something, there was a lot of questions, a lot of doubt. So it meant that if my parents shaped my work ethic and my morals, my PhD advisor shaped my brain as a scientist. He sculpted my brain as a scientist because he insisted on rigor and perfection of data before you make a conclusion. Then I went to Harvard, and my research advisor there taught me research is an exercise in optimism. So it was completely a different message. And you'll get this throughout your life. You'll have different messages from different people. And at the end of the day, you have to decipher what is it that you have learned from these two messages. And what I learned is that doubt asks why. And optimism asks, why not? Okay, you need the two to go hand in hand as a good scientist. You need that optimism to know that there's something that lies beyond all those failures you might have in the lab, that nature is so rich that something lies beyond, which is better than anything you have ever imagined. And you need the doubt to make sure that it's grounded in great science and rigor. So these things go hand in hand. So then I interviewed at Berkeley for a position, for a professor position. I interviewed at Berkeley, I interviewed at Columbia, Maryland, Utah, there's another place, Arizona State, and Georgetown, Arizona State. And Berkeley and Columbia didn't believe what I was proposing that would be possible. Okay, they were very doubtful. I didn't get the job, needless to say. But in the end, I visited Arizona State University for an interview. I liked it. They gave me everything that I wanted in terms of a startup, and I went there. This is a beautiful palm walk that I used to enjoy walking. I was there for 7 years. But there, I was not afraid to ask a big question, a daring question. I have nothing to lose. I have freedom now. I have a position, I have a lab, and I have freedom for the very first time in my life to do whatever I want. And here we ask a very important question that was, everyone is looking at molecules and how molecules interact through weak interactions. Well, that's life, that's our body, that's the living systems. That was the whole chemistry community is focusing on weak bonds. We wanted to ask the question, well, what happens if molecules start interacting by very strong bonds? What could happen? This is why Berkeley didn't give me a job, because everybody, not just Berkeley, but the entire chemistry community thought it was a pointless question, because it's not going to work. When you start connecting molecules together to make larger and larger objects, they become extremely disordered and very difficult to deal with and intractable. So everyone, all chemists, it was really a point of faith, basically, that this will not work. But I have nothing to lose. When I started in 92, I was 26, 27 years old. So I don't have anything to lose, to try. So we tried, and it's a long story, but we succeeded in taking inorganic building units and stitching them together to make completely new kind of materials. We made the very first porous metal sulfides that way. And we published them in extremely high impact journals such as Science and JACS, a flagship journal in chemistry. I was just an assistant professor. And here we opened the door on these completely inorganic frameworks, and we got this strong bond approach to work. And so I thought, that's my destiny. That's the field that I'm going to develop in the future. Until this student came to me, her name is Guanming Li. She came to me and said, Professor, I want to join your group. And I said, no, I don't want you, because her English was not so good. I didn't think she was very strong candidate, and I really didn't have patience to deal with this. And I said, no, you don't. You want a more established professor who could write papers with you very quickly and develop your career very quickly. We don't have to deal with somebody who's not even tenured. I was not tenured at the time. She absolutely insisted and will not go away. So finally I said, I don't know, maybe I'll give it a try. Well, then she started playing with these things. She started taking metal ions and connecting them with organics. So far, I was avoiding organic chemistry altogether. I was really an inorganic chemist by training. And she would show me things like this, and I would keep pushing. In fact, as I walk through the palm walk to go to the gym in the middle of the day, she would jump out of the bushes and show me this stuff. And I would keep pushing her away. Finally, we have, as mentors, we have an obligation to publish what our students' findings, if they are based on sound science, good science, we are obligated to sit down with them and publish, whether they're high impact or low impact. If that's what the student has, we should publish their work. Finally, as we were writing this paper, I realized that there's a huge opportunity that no one has explored, which is that instead of neutral linkers, you could have charged linkers. And if you have charged linkers, you could make, I'm a little too fast. It turns out the reason I didn't like these is because there are a dime a dozen, and although they were beautiful, they were frail structures. They're open structures, as you can see, but when you try to use this porosity to incorporate other molecules, they collapsed. So they were architecturally frail. And that's why I kept pushing her away, because I didn't really have an idea of how we can overcome that. But finally, while writing the lesson here, again, great things come from sometimes very humble beginnings. And this was a very unexceptional result. But nevertheless, it triggered something in our mind on what is the path that could transform this field. And that was charged linkers. When you have a charged linker, negatively charged linker, and the metal ion, which is positively charged, create strong interaction. Now you have a strong bond, and potentially you can make that was our idea, you can make a robust structures. And so I always tell my students to look into the eyes of this beautiful lady, Marie Curie. And this portrait actually hangs in my conference room where I talk to students. And I very often, when things are not going very well, I say, well, look into her eyes and tell me what she's thinking. And you can do more and you can do better. That's really has been my life, that never to be satisfied where you are. You can always do more and you can always do better. And that's what I learned, and that's what I try to teach my students. What happens when you start linking things by strong bonds? You make crud, you make ill-defined materials, you make stuff that is intractable. To make it tractable, you have to satisfy two things in order to make a crystal, which is sort of the target here. The building blocks have to come together, but also they must separate. The reason they must separate and come together and separate again is that they want to find the exact orientation that makes them perfectly oriented with respect to each other. So if they just come together and they get stuck together and they cannot separate, then they're stuck sometimes in the wrong position that starts an avalanche reaction to make intractable materials. And then this process has to be of the right kinetics to allow you. If it's too slow, then you don't grow the crystal large enough. If it's too fast, you make the disordered stuff. So we had to play with the chemical conditions to find the right conditions. And sure enough, Guanming succeeded in making the very first metal organic framework. And that's what the Nobel Committee credited the Nobel Prize for the development of metal organic frameworks. This started a whole field. And then another student came in, a student that, by the way, when I was a student, I was a visiting scholar in China, in Nanjing University, and I met Talian, this student, and we became friends. And when I became professor at Arizona State University, he said he wants to do his PhD with me. Well, so I brought him in, and he was my own graduate student. He found the recipe that is still used until today to make MOFs. Okay, and so we made MOFs that were architecture robust, and we showed that in fact they are by what is called gas adsorption isotherm. That means these experiments show that in fact the stuff that fills the pores of the MOF can be removed without the structure collapsing. So it has permanent porosity. Just like this room, when you leave the room, it doesn't collapse because architecture robust. And that we did on the molecular level. And the person that measured this was Mohammed Adaudi, who, when I was at a conference in Lyon, I missed my lecture because I overslept. And they were very worried that I may have gotten ill or got stabbed on the way to the hotel the night before. And they sent Mohammed Adaudi to fetch me. And while he was walking with me to the conference, he asked me for a postdoctoral position. And I gave him a postdoctoral position, and he did this experiment. By the way, these two people were two of the 14 official guests of the Nobel ceremony, because they are the ones who opened the field. And so Halian made not just those, but he made the compound that became iconic in MOF, called MOF5, made from tetrazinc units linked by organic. And the yellow ball, we put it there because Arizona, at the time, Arizona State used to have in its logo a very nice sun, yellow sun. And so we thought, okay, we'll put the yellow ball there to show the space within which one can bind molecules like hydrogen and CO2 and so on. This turns out to be the compound that everybody credits for the beginning of MOF chemistry. Why? Because it has an extremely high surface area. It turns out that its surface area is equivalent to 2,900 meters square per gram. So that is 5 times the previous record. So we were breaking a 1,000-year record of porosity. And so as an assistant professor, I was absolutely terrified to publish this work, because I was thinking, if I screw this one up, that's it. No more. No more academia, right? And so we verified this, of course, over and over again independently at our university, at even a company, and thankfully it was right. Now, why is this important? Because that surface area in 1 gram of this material, which is like a gram of sugar, of a sugar cube, or is a sugar cube, encompasses as much space as an entire football field. Take a football field, imagine, and fold it, keep folding it onto itself until it is the size of a sugar cube. And that's the space that we have encompassed in this MOF. That was a revolution, and it became a sensation around the world, started a chain reaction of people working on MOFs, investigating MOFs, making more MOFs, studying their properties, studying their applications. So this is what, for those of you who are interested in a nice little movie, the crystals look like this. And as you zoom in on a granule of these crystals, you find that on the atomic level, the structure is really like basically a building or a scaffolding that encompasses space, into which one can compact gases, almost like bees on a honeycomb, so that they occupy smaller volume without having to use high pressure or low temperature. That's basically the operation. And so based on this concept, bees on a honeycomb, we can invent MOFs that in a gas tank like this filled with MOF, you can store 18 times the amount of CO2 than a tank that doesn't have it. Even though the MOF occupies space, but because of those pores, attracting CO2 to the pores better than CO2 to itself, you can compact it into one. So clearly this has tremendous applications. And so we worked with BASF to make a methane storage car. This car gas tank is no larger than the one that uses petrol, and into it you can put MOF powder, and this car can travel 3 times the distance with the MOF than without the MOF. And it was the reason I have this picture is that a German explorer drove a version of this car all over the world, in North America, South America, Europe, Asia, and Africa, to make sure that the MOF can survive the journey of fueling along the way with different natural gas sources, methane sources, because they have different contaminants. So at the end of this journey, the MOF was beautiful, still operated, and so it it can remain in the car for the lifetime of the car. Well, again, I will mention some people that I met along the way. Ulrich Müller, when I first reported the very high surface area of MOFs in a German zeolite conference, everybody didn't believe it. Really, the German professors up front stood up and really was very upset about it. But Ulrich Müller was different. After my talk, he came to me and said the number was so unbelievably high, I thought it had to be a misprint. And so he's a chemist at BASF. He started reproducing our work. And I had to make sure with Halian that our prep be described exactly as we did it, such that a high school student can repeat it. Halian said, Professor, we should not give secrets to the world, otherwise they become competitors. And I said, no, we will report it exactly as it is. That's how science works. And that actually was a very fortunate thing that we did, not just good science, but good strategy to get everybody to plug into MOFs. And it became a whole field. And so they were reproducing our work successfully, and they were getting higher surface area than ours. Okay, they had been evacuating the pores a lot more efficiently than we have. And in fact, that number was much higher than 2,900 meters square per gram. It was 4,000 meters square per gram. So it was amazing, and that began a collaboration with BASF, and very quickly, we took the MOFs from the laboratory to industry, and they scaled them up to ton scale within a few years. Now the field became, people were criticizing, obviously, right? You always have detractors. People saying, oh, these are boutique materials. These are never going to see the light of day in applications and so on. So I needed a large chemical company like BASF to invest in MOFs and show that, in fact, these can be made in multi-ton quantities, and they can be made using sustainable and benign chemical conditions. So not only can you make them, but you can modify them. You can make the pores larger. You can make it smaller. You can make it as small as to fit hydrogen molecules for hydrogen storage, or you can make it as large as to put an enzyme in there. So all of that is possible. And so you can imagine a whole fields of use have emerged because we can control matter on the atomic and molecular level. And when you look throughout history, whether it's the Stone Age or the Brass Age or the Iron Age or the Glass Age or the Pharmaceutical Age or the Silicon Age, not only do we name our civilizations after those ages, after those materials that we use, but also the more we can refine them and design them on a finer and finer level, the larger our economies became. And the more people have benefited. And the ultimate design, the ultimate precision is on the atomic and molecular level. Well, that's MOFs. So the first application came from a colleague of mine at the University of Calgary. And we have a MOF that is deployed in cement plants. Cement plants pollute the air. They contribute to 1/3 of the CO2 emission of industry. And this MOF is now in 3 plants capturing CO2 from flue gas before it reaches the atmosphere. So this is great, and BASF is scaling up the MOF to hundreds of tons for this application. I want to tell you about a development here in Berkeley. My students made a material, it's not a MOF, but a COF. There's another generation of materials that Nobel Committee didn't cite, because maybe there would be another Nobel for these materials, okay? But these are COFs, they're very stable, and we can use them to capture CO2 from Berkeley's open air. It's a yellow powder, and you can see here that the air in Berkeley has over a 20-day period, which is the experiment time. We did it over 20 days. You can see the concentration of CO2 in the air is about 450 ppm. We measure the relative humidity in the air, and we measured how much the CO2 being taken up by the material. It turns out the material takes up all the CO2 that's in the air. You take Berkeley open air and pass it through the material, and on the other side, you have no CO2 coming out, trapped into the pores. This is quite transformative. This is the only material, this Berkeley material is the only material out there that has the best commercializable performance for capturing CO2 from air. So, CO2 capture from air at scale, we have 1,100 gigatons of extra CO2 in the air that we need to capture. This is the extra stuff we put into the air since the Industrial Revolution. Using our material, you need 100,000 tons of cough to capture half a gigaton of CO2 every year. That will take us 2,000 years. But if we put such a plant in every city where you have 1 million people or more, we can do it in 3 years. Without changing the material. This material is based on strong bonds, and so it can stay in the plant for years, right? And before you say, well, Professor, that's a lot of material. Well, but chemical industry is used to producing lots of material. 200 million tons of sulfuric acid every year is being produced. So this is at the scale that chemical industry can produce. The cost, the DOE target is $100 per ton. And so it will cost us to remove this 1,100 gigaton about 100 trillion worldwide. That's the world's GDP. Okay, again, before you go crazy over this, that just means that if we use 4% of the world GDP to do this, it would take us 25 years, which is not bad. I mean, we spend more than that on defense, less than that on education. So I would say that this is very doable, and especially since we're already spending trillions on the effect of climate change, on the severe weather patterns and producing destruction. So I think that this is very doable. Of course, it requires at least the G20 to come together and think about it as a crisis to solve it. I don't think one country can solve this problem. I think it needs at least the G20. But here's a solution. The scientific solution is here, right? And what I didn't tell you is that we're only using 20% of the COF capacity, the materials capacity. So if Zihui, who is working on this, can double the capacity, well, all these numbers fall by half. That's the power of controlling matter on the atomic and molecular level. Okay, another application that I want to discuss is taking water from the air, especially arid air, and making drinking water. So we design MOFs that can do that. And I'm going to show you inside the pores of one of these MOFs. It's an aluminum MOF that takes up water first into the hydrophilic sites. And then when those hydrophilic sites are filled, it bridges over hydrophobic sites and fills the pore. So the great thing about this is that I realized when I looked at this data that we can take the water out at 45 degrees C, which is exactly the temperature in a midday in the desert. And that really made me realize that we can use this for water harvesting and for drinking. Now, the question is, would I have seen that in the data had I not lived it first? That's why I think mixing researchers is so important. Okay, so my students, my heroes, took this to the desert, to Death Valley, to show that, in fact, it works there. And you can see here a device made from MOFs is harvesting water from air and producing water with no energy input aside from ambient sunlight. Now, in this year, we will have devices that produce 2,000 liters of water at 0.3 kilowatt hour per liter, okay? But also, we have ones that don't use any energy or electricity. It only works on waste heat and ambient sunlight, and those will deliver about 850 liters per day, every day, for years, for 6 to 7 years. And at the end of the MOF journey, we can separate the metal from the organic and reassemble them in water in zero discharge process. Okay? So this is really a game changer, and it will give my dream of having everyone have water independence in the world, okay, where your water is yours, independent of everything else. Okay, I have probably 2 more minutes that I can share with you. Okay, so we've invented this field, MOFs, and I didn't discuss COFs except for CO2 capture, but we also are looking at a new field that we have invented here at Berkeley in collaboration with Professor Jennifer Shays, the Dean of CDSS. And we call it ametry. Ametry is crossing AI with materials and chemistry. Okay, this is a field that is still in its early development, but as you know, there's a revolution in AI, and we want to plug into that revolution to work on speeding up discovery of materials. And here, I just want to show you one example of how powerful LLMs can be. So here's a COF. A COF is an all-organic porous structure, just like the ones I've been describing. No metals here. And over the last 10 years, many groups have tried to improve the crystallinity of this COF without success. So we said, okay, let's use ChatGPT to help us with this. So the students wrote like a page and a half of prompt. You are a reticular chemist, that's our brand of chemists, we call it reticular, developing beta-ketoenamine COF. We have a robotic platform that will execute the experiments, and so on. Your task is to conduct literature investigation of COF, synthesis, and develop reaction conditions. This is what a researcher does. That's what the students are supposed to be doing. Generate a table, okay? Initial 96 conditions because of the wells, and then select precursor. You understand. Select the conditions, check for accuracy and reproducibility. Okay, and create a list of references. So basically, the researcher does nothing except ChatGPT does it for you, which I think it's absolutely fantastic. And so ChatGPT gives you a bunch of conditions under which you should be able to crystallize this material. And the robot does it for you, right? The robot will fill the wells and so on, and you can incubate, wash the sample, and analyze it by X-ray diffraction, and then feed the results back into ChatGPT and continue to go around this cycle. So the student only did 3 cycles, right? And obtained not just one crystalline material, but many, many conditions under which he has highly crystalline material, 3 times better than what was in the literature. Okay, so you can imagine I'm really excited about this, and I have switched my whole group to work on ChatGPT and on generative AI and on machine learning, and nobody in my group is not doing that. So everyone is blending experiment with AI, and it's transforming everything that we're doing. We're building a molecule to society engine where you predict, then you go to the lab and make, and then scaling and commercialization. All of those work together, will work together in the fullness of time. Okay, the results. We can double the rate of discovery in my lab compared to conditions, compared to students that are now using machine learning. Okay, so these are my former students who, as I said in the Nobel lecture, who fail and fail and fail so that they can succeed. They are my heroes, visiting scholars and others who have come through my lab. And you should always try to look for people who love you just a little bit more than everybody else, who embrace you a little bit more than everyone else, because those are a treasure in one's life and one's journey. And these are, I have more, but I think these are the ones that I feel very close to, and they have helped me along the way. And my current group members, see, they're all very happy. And financial support by government and non-government agencies. And I want to thank you for listening to me.
Thank you so much, Professor Yaghi, for your talk. We'd like to give a few minutes just for student questions. We're going to have, and then we'll switch to the next speaker right after that. We're going a little bit into the break, but it's okay. Our reader UL has a microphone. So if you have a question, please raise your hand and he'll throw the microphone to you. In the back.
Hi, Professor. Thank you so much for the lecture. I just have a question on your previous slide about like asking ChatGPT for reproducibility. I was wondering, like from your personal experience, how reproducible are actually these recommendations given by ChatGPT? Because given like kind of the nature of chemistry is a lot of experiments where even like kind of the experimenter can't really reproduce.
Well, once you identify the conditions to make crystals, it doesn't have, ChatGPT doesn't have to be reproducible. The chemistry under those conditions has to be reproducible. So I don't really care how much ChatGPT evolves over time. As long as I've identified the conditions under which to make something, and then those conditions are reproducible in the lab, then I have nothing to worry about. By the way, I will be hanging out in the hallway for a few minutes afterwards in case you have further questions and you don't get to ask.
Here? Good. Hi, Professor. Thank you for the lecture. I was wondering on the speed in which these MOFs capture different molecules. For example, could they be used in an emergency to, capture smoke particles or whatever, or let's say to defend against some chemical warfare or something?
Yeah, very good question. We measured how fast water goes through a crystal, and it turns out it's nanoseconds, extremely fast. Because when you think about the MOF, it's really a scaffolding. So it has pores, but no walls. And so things can diffuse in and out with many different pathways and very fast. Yeah.
One last one. Actually, maybe we can do one in the front.
Hi, Professor. So you mentioned how you're using AI at every step in research now. So what role do you see human intelligence playing in the future of research if AI can do it all?
Well, I think AI is going to replace most of what we do, leaving us some time to think about, analyze data and think about new directions and create new things. AI will take up it will create, I think, more jobs for chemists. But I think at the end of the day, it will replace a lot of the trial and error methods that we rely on so much. And we're very biased beings. We are extremely biased. For example, a lot of stuff that used to go on in my lab, students would take 3-4 years to crystallize a cough. It's because they were advised by me or by fellow graduate students on certain conditions that work and certain others that don't. And therefore, we were exploring only a small part of the space that we should be exploring. ChatGPT now can tell us what's happening beyond that small space. So I think, to me, a lot of aspects of AI are very strong for the development of science. And of course, there are harmful aspects, but that we can think about. When we're doing these models, we need to build into them some kind of stops or guardrails for that. But for us in a university, we should be thinking about how to advance the frontiers of knowledge and how AI could be used to speed up that and to induce us to ask new questions.
Thank you, Professor. So other than chasing you down during the break, how can students get involved in this type of research or with your lab?
I think the best way to get involved is to try to, there are several ways. You can, if you have a TA, a GSI, teaching assistant that you work with in one of your classes, they could give you some good advice on how to approach a professor. You can always write an email to professors. I'm not sure how successful that would be. I think it depends on how clever you are in writing.
After you.
And convincing, how convincing you are in writing that email. All of us professors are very interested in having undergraduates in our lab. I have 4 or 5 almost always. And because it's part of our mentoring mission, But we need to be convinced that that student is going to be learning rather than just spending time to get a recommendation letter. Obviously, you will get a recommendation letter if you're learning and participating. So we want to see you participate and grow from the experience. And I think that's everybody's door is open to that.
You've been listening to Berkeley Talks, a UC Berkeley news podcast from Strategic Communications at Berkeley. Follow us wherever you listen to your podcasts. You can find all of our podcast episodes with transcripts and photos on UC Berkeley News at news.berkeley.edu/podcasts.